Hello friends, welcome to the lecture on reactions of carbohydrates. The first part, here we'll be taking oxidation of carbohydrates and particularly glucose. Now glucose, as we all know, has the suffix "ose", and the most common carbohydrate with the molecular formula C6H12O6. Applying the terms defined above, glucose is a monosaccharide, an aldohexose, and a reducing sugar. The general structure of glucose and many other aldohexoses was established by simple chemical reactions, which we'll be taking in the next slide. So glucose C6H12O6, the first reaction when the reaction is with HCN, it forms a cyanohydrin. On oxidation with bromine water, it forms a acid which is gluconic acid. On oxidation with dilute HNO3, glucanic acid is formed. With reaction of HI, and when we heat glucose, hexane is formed. On reaction with sodium borohydrate, a sorbitol is formed, and excess of acetic anhydride in pyridine, a hexaacetate is formed. When we take only excess of acetic anhydride in pyridine, a pentaacetate is formed. So these are the simple reactions like oxidation, reduction, and with sodium borohydride or acetic anhydride. So what are the possible products that are formed? They are shown here. Hot hydroiodic acid, HI, was often used to reductively remove oxygen functional groups from a molecule, and in the case of glucose, this treatment gave hexane. So here we see removal of oxygen functional group is reduction. So this reaction is a reduction reaction and it forms hexane. From this, it was concluded that the 6 carbons are in an unbranched chain. So glucose is an unbranched chain of 6 carbon atoms. The presence of an aldehyde carbonyl group was deduced from cyanohydrin formation. Its reduction to the hexaalcohol sorbitol, also called glucitol, and mild oxidation to the monocarboxylic acid, glucuronic acid. Somewhat stronger oxidation by dilute nitric acid gave the diacid glucaric acid, supporting the proposal of 6 carbon chain. So here are the different oxidizing agents that in the presence of which acid or which type of reagent, what kind of product we get. Stronger oxidation by dilute nitric acid, a diacid is produced. So different products are seen here. The 5 oxygens remaining in glucose after the aldehyde was accounted for were thought to be in hydroxyl groups, since a pentaacetate derivative could be made. So there are 5 hydroxyl groups, like 5 oxygens which are hydroxyl in nature, and therefore they form pentaacetate derivative. Other important reactions. Emil Fischer made use of several key reactions in the course of his carbohydrate studies. The first one is oxidation. Sugars may be classified as reducing or non-reducing based on their reactivity with Tollens, Benedict's, or Fehling's reagents. If a sugar is oxidized by these reagents, it is called a reducing sugar. Since the oxidant, the silver ion or the copper ion, is reduced in the reaction, as evidenced by the formation of a silver mirror or precipitation of cuprous oxide. The tolerance test is commonly used to detect aldehyde functions. And because of the facile interconversion of ketoses and aldoses under the basic conditions of this test, ketoses such as fructose also react and are classified as reducing sugars. When the aldehyde function of an aldose is oxidized to a carboxylic acid, the product is called an aldonic acid. So here aldonic acid is the result of oxidation of only the aldehyde function CHO. Because of the secondary hydroxyl functions that are also present in these compounds, a mild oxidizing agent such as hypobromite must be used for this conversion. We'll be seeing in equation 1 in the next slide. If both ends of an aldose chain are oxidized to carboxylic acids, the product is called an alderic acid. So alderic acid is a diacid. By converting an aldose to its corresponding alderic acid derivative, the ends of the chain become identical. This could also be accomplished by reducing the aldehyde to CH2OH. So the primary hydroxyl group, if is formed by the reduction of CHO, we get similar terminal groups. Thus ribose, xylose, allose and galactose yield achiral alderic acids, which are of course not optically active. The ribose oxidation is shown in equation 2 below or in the next slide. Here we see D minus ribose, presence of hypobromite. It forms ribonic acid. It means the aldehydic group is converted into a carboxylic group. The second one is D minus ribose in presence of nitric acid. Here we see that both the ends are identical functional groups. This is a diacid alderic acid, but it is optically inactive since it forms a mirror image. So this is optically inactive compound. And here we have D minus arabinose. On oxidation, it forms D-arabinic acid or D-laxaric acid, and this acid, laxaric acid, is also formed by oxidation of D minus laxose. So other aldose sugars may give identical chiral alderic acid products, implying a unique configurational relationship. So here we have taken the oxidation of glucose with different oxidizing agents or different sugars also, which form where identical diacid, but they may be achiral in nature. Thank you.